You've been told all your life that blood is red. It's a fact so basic that we barely think about it, until a scraped knee or a small paper cut reminds us in vivid crimson. Bright red blood is so fundamental that even children memorize it in school. Arteries carry red blood, veins carry blue. Look down at your wrist. A network of lines, undeniably blue, snakes beneath your skin. It seems obvious. Oxygen-rich blood flows out in arteries. Oxygen-poor blood returns in blue veins. Our diagrams, textbooks, and everyday observation reinforce this. Logic appears to confirm the color division, yet appearances deceive. Blood drawn from these supposedly blue veins is dark maroon red, deep, rich, and unmistakably red. So why do our eyes perceive blue? The answer is found not in the blood, but in physics, light, and human perception. When sunlight or artificial light hits your arm, it penetrates skin layers differently. Red light, with its long wavelength, penetrates deep into tissues, while blue light, short and energetic, scatters near the surface. Dark, deoxygenated blood absorbs red light, allowing predominantly blue light to reflect back. Our brains interpret this red deficit as blue. The veins themselves are not blue. It is a trick of optics, a combination of physics and biology conspiring to mislead our senses. The lesson here is subtle yet profound. Our perception is a filter, and science is the lens that reveals truth. This simple optical illusion sets the stage for a far more extraordinary reality. Blood is not merely red. It is a microscopic dance of chemistry, physics, and evolution, a story older than humanity itself. To understand blood's red color, we must shrink to a microscopic scale. Within a single drop of blood exists a bustling universe of cells and molecules performing tasks vital to life. The primary actors are the red blood cells, biconcave discs perfectly engineered for gas transport. But the real secret lies in hemoglobin, the protein packed inside these cells. Hemoglobin is a molecular machine, intricately folded and structured around the heme group, which contains a single iron atom at its core. Iron, a metal forged in the cores of massive stars, forms the heart of the molecule. Iron is no mere coincidence. It is a cosmic gift. Supernovae, the explosive deaths of massive stars, scatter iron across the galaxy, seeding planets like Earth. Every atom in your hemoglobin is literally stardust, the universe's material shaped over billions of years into life itself. The chemistry is elegant. Oxygen binds to the iron atom, changing the molecular conformation of hemoglobin. When oxygen-rich, oxyhemoglobin, blood reflects a bright scarlet red. When deoxygenated, deoxyhemoglobin, blood shifts to a dark maroon, almost brown. This dynamic shift occurs continuously, with trillions of red blood cells cycling oxygen every minute. A microscopic ballet ensuring tissues receive life-giving oxygen. Historically, the discovery of hemoglobin and its oxygen-carrying properties was monumental. Scientists like Felix Hoppe-Seyler and Max Perutz uncovered the molecular basis of blood color, revealing a connection between chemistry and life that we now take for granted. Blood, then, is not just a color, it is chemistry in motion, life encoded in molecular design, and a physical link to the cosmos itself. Each drop of blood tells a story of constant motion. A red blood cell leaves the lungs, saturated with oxygen, a crimson jewel racing through arteries to deliver life. As it reaches tissues, hemoglobin releases oxygen, darkening to maroon, and travels back to the heart via veins. This journey is not just a matter of circulation, it is a symphony of timing, chemistry, and physics. The heart pumps with precise rhythm, valves ensure one-way flow, and blood vessels of varying elasticity regulate pressure. Even slight variations, like oxygen availability or blood pH, subtly affect hemoglobin's ability to bind oxygen, demonstrating the delicate chemistry underpinning life. In conditions like methemoglobinemia, a mutation in hemoglobin's iron structure prevents oxygen binding effectively. The result is chocolate brown blood, sometimes visible through skin as a bluish tint. A single atomic level change cascades into a dramatic physiological effect, illustrating how blood color is a direct reflection of molecular integrity. Blood has long captivated human imagination. Its color, life-giving properties, and visibility in injury and ritual have inspired myths, religion, and art. Ancient Egypt, blood symbolized life and divine vitality. Sacrificial rituals and ceremonial symbolism often depicted red as sacred. Aztec civilization, blood was a medium to sustain the gods and the sun, connecting the mortal and divine. Greek philosophy, blood's red hue represented courage, passion, and soul force. Philosophers like Galen speculated about its role in temperament and emotion. These symbolic interpretations were, unknowingly, rooted in biological observation. Ancient humans recognized blood's centrality to life and connected it to broader metaphysical and cosmic ideas, a reflection of instinctual understanding preceding formal science. Humans are red-blooded, but evolution has painted alternative solutions. Some ancient animals, like octopuses, squids, and horseshoe crabs, use hemocyanin, a copper-based oxygen carrier. Copper, when bound to oxygen, turns blood sapphire blue. Deoxygenated hemocyanin is colorless, but oxygenation triggers a striking blue appearance. This adaptation evolved to optimize oxygen transport in cold, low-oxygen environments, such as deep seas. The horseshoe crab is particularly fascinating. Its blue blood contains amebocytes, cells highly sensitive to bacterial endotoxins. Today, these cells are critical in the LAL test, ensuring the safety of vaccines, medical devices, and implants worldwide. Humanity's medical safety relies on this ancient, blue-blooded creature, illustrating an unexpected intersection of evolution and modern science. Beyond red and blue, nature's palette surprises us with green blood, most famously in certain skinks from New Guinea. These reptiles carry red hemoglobin like humans, but their plasma is saturated with biliverdin, a green bile pigment that in humans would be toxic. Why green? Evolution turned a waste product into an advantage. High biliverdin levels make the skinks unpalatable to predators, serving as a chemical defense. It also appears to reduce parasite loads, a fascinating adaptation where the byproduct of one system becomes a survival tool in another. Imagine the blood flowing through these lizards, deep red from hemoglobin, tinted vividly green by biliverdin, a living demonstration of evolutionary creativity. It's a reminder that life doesn't always follow human logic. It finds solutions wherever chemistry allows. Even in humans, we see hints of this palette. Bruises transition from red to green as hemoglobin breaks down into biliverdin before finally turning yellow, bilirubin, and fading away. A bruise, in a sense, is nature's miniature visible chemical show, reflecting the dynamic biochemistry beneath our skin. In the depths of the oceans, some marine worms display violet blood, a color created by hemorrhithrin, another iron-based oxygen-binding protein, but with a structure distinct from hemoglobin. When oxygenated, hemorrhithrin turns pinkish-violet. When deoxygenated, nearly colorless. Unlike hemocyanin or hemoglobin, hemorrhithrin lacks heme groups, highlighting how molecular variations produce entirely different colors while performing the same life-critical function, transporting oxygen. The diversity of blood chemistry is a testament to life's ingenuity. Evolution experiments with different metals, structures, and protein folds to adapt to environmental pressures, from icy polar waters to oxygen-poor ocean trenches. Each blood color reflects an intersection of chemistry, physics, and survival strategy. The Antarctic icefish, or Channicthidae, is perhaps the most radical blood adaptation. Adult icefish have no hemoglobin at all, and in some species, even the heart pumps watery, clear blood. Survival is possible because Antarctic waters are exceptionally oxygen-rich, especially at near-freezing temperatures, allowing passive oxygen diffusion through tissues. To compensate, ice fish have evolved enlarged hearts and vast blood volumes to circulate sufficient oxygen. This adaptation is astonishing. Life thrives without the very molecule we consider indispensable. Transparent blood is a living paradox, challenging our assumptions about biology. It's an extreme reminder that evolution prioritizes function over convention and that life finds a way even by breaking the rules. Returning to humans, the red in our veins owes its hue to iron, a metal forged in the cores of massive stars. When such stars explode as supernovae, iron spreads across galaxies, eventually forming planets, crusts, and life itself. Every red blood cell is a microcosmic link to the cosmos. Each iron atom in hemoglobin has traveled billions of years across space, shaped by nuclear fusion, scattered in explosions, and finally incorporated into our bodies. This is more than poetic. It's a scientific fact. Red blood, at the elemental level, connects us to the life cycle of stars, tying human physiology to cosmic history. Each heartbeat is, in essence, a rhythm set by the universe itself. Blood is more than pigment and protein. It is meaning, connection, and narrative. Its color, behavior, and variations remind us that life is diverse, adaptable, and deeply creative. Red, humanity's star-forged essence. Blue, evolutionary ingenuity in invertebrates and cold oceans. Green, chemical defense in skinks. Violet, hemerythrin-driven oxygenation in marine worms. Transparent, Antarctic ice fish's extreme adaptation. Each hue tells a story about how life solves problems, navigates chemistry, and embraces environmental constraints. Blood reflects both the universality and individuality of living systems. Blue blood isn't just an evolutionary curiosity, it has practical implications. Horseshoe crab blood contains limulus amoebocyte lysate, LAL, which reacts to bacterial endotoxins. Today, LAL tests ensure the safety of vaccines, injectable drugs, and medical implants worldwide. Meanwhile, humans rely on synthetic iron supplements, transfusions, and hemoglobin-based therapies to manage diseases like anemia or hemoglobinopathies. Blood's color and chemistry are not merely aesthetic. They are directly tied to survival, medicine, and technology. Even green-blooded lizards, once considered a curiosity, inspire biomedical research, as their resistance to biliverdin toxicity may offer clues for managing bilirubin-related liver conditions in humans. From a macro perspective, blood is a story of evolution in action. It demonstrates diversity, multiple chemical solutions for oxygen transport, adaptation. Each pigment is optimized for environmental conditions. Ingenuity. Waste products become defenses. Molecules take on unexpected roles. Resilience. Life can thrive even in extreme or seemingly impossible conditions. Blood is a mirror of life's complexity. The blue veins on your arm are optical illusions, not reality. Human blood is always some shade of red, oscillating between maroon and scarlet, powered by iron atoms forged in stars. Across nature, blood displays an astonishing palette of colors: blue, green, violet, and transparent, each with unique chemistry and evolutionary logic. Blood connects the microscopic to the cosmic, physiology to philosophy, and survival to storytelling. In essence, blood is life in motion, a chemical symphony, and a cosmic inheritance. It reminds us that the ordinary often conceals the extraordinary, that science reveals layers of wonder beneath what we take for granted, and that life's solutions are limited only by chemistry and imagination.
If you want more hidden truths about life, chemistry, and the cosmos, subscribe to Infinite Archive. What everyday facts do you think hide extraordinary stories? Share your thoughts in the comments below.